How do ceramics creep and fail at extreme temperatures? Have you ever wondered how ceramics, known for their strength, can still fail when exposed to extreme temperatures? It might seem surprising, but even these tough materials can experience issues under certain conditions. Let's break it down. Ceramics are famous for their high melting points and durability. However, when they are subjected to extreme heat and continuous stress, they can undergo a process called creep. Creep is a slow, time-dependent deformation that occurs over time. This usually starts at temperatures above about half of the melting point of the ceramic material. Below this threshold, the material remains relatively stable. As temperatures rise, atomic diffusion becomes more significant. This means that atoms within the ceramic can start to move around more freely. This movement can happen within the crystal lattice or along the boundaries where grains meet. Over time, this can lead to permanent deformation. There are two main mechanisms that contribute to creep in ceramics. The first is diffusion-assisted grain boundary sliding. This involves the grains of the ceramic sliding past one another, which can cause elongation without immediate fracture. The second mechanism is dislocation creep, where line defects in the crystal structure move under stress, leading to plastic deformation. Several factors influence how ceramics behave under stress and heat. These include grain size, the amount of stress applied, the temperature, and how long the material is exposed to these conditions. Unlike metals, ceramics do not show significant plastic deformation before they fail. Instead, creep can lead to microcracking and separation at grain boundaries, which can weaken the material. As these microscopic damages accumulate, they can cause sudden and catastrophic failure. Once the internal damage reaches a critical point, the ceramic can fracture unexpectedly. Interestingly, just having a high melting point does not guarantee that a ceramic will resist creep. Some materials may still creep significantly if their microstructure allows for easier diffusion. This means that predicting how a ceramic will behave under stress requires a good understanding of its specific composition and structure. In practical applications, ceramics are often used in environments like turbine engines or high-temperature molds. Here, they face extreme temperatures and stresses that can lead to creep. Engineers must consider these factors when designing ceramic components to prevent premature failure. To improve creep resistance, strategies can include refining the grain size, adding materials to stabilize grain boundaries, or creating composite materials that combine ceramics with fibers or metals. These approaches can enhance performance at high temperatures. In summary, ceramics can creep and fail at extreme temperatures due to time-dependent diffusion processes and stress-driven deformation mechanisms. Understanding these behaviors is essential for creating durable ceramic components in high-temperature settings and preventing unexpected breakdowns.